Decision trees are useful. They're more than just classifiers. We've presented them as an application of information entropy, but their intuitive nature makes them useful in a large number of applications. So in practice, decision trees have a bad reputation and they deserve it. They do tend to overfit. They can produce arbitrary, even comical sequences of decisions. When they are a classifier, they tend to be very naive. They tend to only be able to handle linearly separable data, and there's really no concept of embedding into higher dimensions or using any of the other aspects that we see in complex data. So why do we use them at all? Well, a decision tree is a graph, so at least we're using some graph theory. It's constructed using information theory. If it's appropriate and doesn't overfit and validates and is otherwise reliable, then decision tree is highly intuitive. It's easy to interpret and it's actually easy to apply. It also is diagnostic. It makes predictions, but it also provides reasons or rules for its predictions. It's not just 1 or 0, it tells us why. So let's first look at why they're useful because they're intuitive. We actually have already seen trees. We use trees to develop ideas about information itself. We can make probability more intuitive using trees. So earlier we showed that the definition of conditional probability, we actually derive this from conditional information. And we can illustrate this same idea again as a branch of a tree. Suppose we have a sequence. First x takes the value x and then y takes the value y. So we've got a probability that we get the little x, a probability that we get the little y given the x, and the combination of the two is the joint probability. So the joint probability is the product of the first branch and the second. Now we'll eventually have a lot of branches, but each branch is mutually exclusive of every other. These are disjoint events. So we can actually add end results of different branches. So let's look at this example of choosing cards. So let's suppose Jane uniformly randomly samples from 0, 1, 2. Then you want to change it up a little bit. I'm going to randomly sample from 0, 1, 2. I'm guessing Jane's card. John then uniformly randomly chooses a card not equal to either mine or Jane's, but then he tells me his card. Then I switch. In other words, the sample will not be equal to John's card or to my first guess. I switch my guess. So X is Jane's card, Y is John's card, U is my guess, and S is the random variable for the switch. So let's illustrate all this with a tree, and we'll actually solve the problem of whether or not to switch. Switching is better than the initial guess in doing so. So first let's look at what happens if my initial guess matches Jane's card. Well, that would happen if I got the same value for the X and the U in 3 different ways, both 0, both 1, or both 2. How can we do that with a tree? Well, first we have Jane, and with probability 1/3, Jane could have gotten a 0, a 1, or a 2. Next we have me, and with probability of 1/3, I could have gotten a 0 or 1 or a 2. So when Jane got a 0, I could have gotten a 0, 1, or 2. And when she got a 1 or she got a 2, likewise, I could have gotten a 0, 1, or 2 in either of those conditions. And my selection's independent of Jane, so I also have a probability of 1/3 in each case. So notice that matching 0 equals 0 is got a probability of a ninth. 1/3 times 1/3. Likewise, the match in the middle has got a probability of a ninth, and the match on the bottom, the 2 and for me and for Jane both, also has a probability of a ninth of occurring. So the probability that I get a match is the three separate paths probabilities added together. They are exclusive. I can't go down one path. If I go down one path, I can't go down any of the others. So that's a ninth plus a ninth plus a ninth, and that's a third. So let's keep going. So does switching have a higher probability than sticking with the original guess U? So we've shown that if I make a guess U, then I have a probability of 1/3 of guessing what Jane's card is with no other information given. But now John comes along and he has to follow a special rule. He cannot pick my first guess or Jane's card. That means if Jane and I both picked a 0, then he could pick her a 1 or a 2, and he could pick either one of those uniformly random with a probability of a half. And then I'll switch. So if I had a 0 and John shows me a 1, then I'll switch to a 2. And now I compute the probability. A third times a third times a half, that's an 18th. Likewise, if I guessed 0, John shows me a 2, and I switch to a 1, that's a probability of an 18th. Okay, but notice that if Jane and I get different numbers, then there's only one thing left for John to prove, to choose. So if Jane chooses 0 and I guess a 1, then John has to show me a 2. He's got no other choice. So there's a probability of 1. And so that switch means that I go to a 0, and I do that with a probability of a ninth. Because I guessed a 1, John showed me a 2, the only possible switch is to the 0. And we continue the same logic throughout the entire tree. And now we can compute the probability that S matches X. So I've outlined in blue those occasions when S matches X. So here are the paths, and you'll notice that there are 6 disjoint paths that I can take leading to the S being the same as the X. There's a ninth for the first path, a ninth for the second, a ninth for the third, a ninth for the fourth, a ninth for the fifth, a ninth for the sixth. So there's 6 ninths, and that's a probability of 2/3 if I switch. So what we've actually done is just solve the Monty Hall problem. It's a very famous problem. People get very confused by it, but you see we have no issues whatsoever because the probability tree has illustrated it completely and clearly. So what is this problem? Well, behind one of 3 doors is a car, and behind the other 2 are goats. You pick a door, and then Monty opens a door with a goat behind it. So he doesn't open your door, but he opens another door with a goat behind it. Should you now pick the other door, the door that's remaining? Well, we just solved this. You have a probability of winning of a third if you stick with your first guess, but a probability of 2/3 if you switch. So if you don't believe me, go back and look at the probability tree. It's as clear as you can get, and demonstrating this outcome. So why do we use decision trees? Well, they're highly intuitive. They're also diagnostic. This is a really important idea. So let's look at an example. Let's predict types of cars most likely to be purchased from the well-known car evaluation data set from the UCI Machine Learning Repository. We've got 6 features for 1,728 models, and if those models were desirable to buyers. Here's the data. There's the cost to maintain, how much luggage space, whether or not they're saved, and then the class is got 4 different possibilities: very good, good, acceptable, and unacceptable. So we're going to find a decision tree classifier that's constructed from the car evaluation data. But we're going to predict if somebody's going to rate a car as very good. So we'll have 2 classes. We'll have cars rated as very good, and then everything else will be considered not very good. There's 35 cars in Class 1 and 1,693 cars in Class 0. So here is our resulting tree. And the key here is, given that this is actually not an overfit or unreliable tree, and the next module will actually show it's a really good tree. And given that, we can actually diagnose what it means for a car to be very good. It's very safe, it's a medium or low price, it has 4 or more passengers, it has sufficient luggage space, and it does not have high maintenance costs. So we didn't just classify, we actually diagnosed what it means to be a very good car. So when we're using decision trees, we need to be willing to reject a decision tree approach and try something else at every step. And I'll actually talk more about this. There are a lot of approaches that end up with decision trees that don't start with them. Validate as you build and test afterwards. Grow larger trees and then prune them back. We'll talk more about that later. And look out for overfitting. And the longer the tree gets, the more likely it is to be an overfit. So let's look at another example, the Wisconsin breast cancer data. There's 2 classes, malignant or benign, 9 features for each patient, and each of the 9 features has a rating from 1 to 10. So here's the data. There's 699 observations, and yes, there's missing data. So we'll have to do some pre-processing before we can construct our tree. We'll have to impute those values. And now here again is rattle. So this is again an R package for data mining. Very nice. I like it a lot. Validation, we got a 5% error. But not only is this a classifier, it's also a diagnostic tool that I can use clinically. For instance, if I have size uniformity less than or equal to greater than or equal to 2.5 and less than 4.5, and the bare nuclei is greater than or equal to 2.5, then the likelihood of cancer is 84%, and there's 9% of the patients that fall in that leaf. We also have neighbors. So everybody who falls into a leaf are similar. So if you go down this table, you actually have a criteria based on these decisions, and if you have you and your neighbor both satisfy the decisions, then you're going to be in the same leaf. Okay? So here it is again with the isotosa, the iris data. And this is how you could use a decision tree for something other than classifier. For instance, you could look at regression. Once you get to a leaf, you predict a value that's the, for example, average or regressed value from the neighbors. Now, of course, if we just use a single decision tree, then the neighborhood graph is going to be disconnected. There are going to be clusters for every leaf, but all the leaves are not connected to each other. But what if we use several trees? Well, this is exactly what we do when we use what are called random forests. And no surprise that the outcome of random forest is a pretty darn good nearest neighbor graph. So decision trees and nearest neighbor graphs both are important, both are useful, both occur abstractly and concretely in other algorithms. They have their issues. But decision trees and information, very intuitive, great for explaining your results to a client, for example. We'll look at some extremely powerful algorithms, but eventually you have to tell somebody what's going on, and that's often done with things like neighborhood graphs and decision trees and visualization tools. And because they're very intuitive, that makes them very useful.